This is people. This is Piero Dincheco. Did I pronounce that right? And Piero works for the Italian National Institute of Astrophysics, or for Astrophysics, and is here talking to us about geological mapping on Venus. Piero, we are all yours.
Hello, everybody. And I'm going to now to share the screen. Yes, as Carlos has mentioned, I'm now working at the Observatory of Abruzzo for the National Institute of Astrophysics in Italy. And I am now going to talk about the geologic mapping on Venus. Can you all see the presentation?
Yes, we are seeing though the whole PowerPoint. Not
okay, great.
Okay.
Yes, yes. So I will be giving now today a presentation, a seminar about geologic mapping on Venus, because Venus has been for long considered, of course, as the hellish twin of our planet, just because it appears very similar to Earth in terms of dimensions, and of course also it has an atmosphere. But it differs from Earth because of the hellish conditions at its surface, because of the very high temperature, I mean 475 Celsius degrees on its surface, and also for the thick atmosphere, which gives a pressure, an atmospheric pressure of 90 bars on the surface. So it's a very hellish twin of planet Earth. And mapping the surface of Venus is a bit different than mapping, for example, on Earth or other planetary bodies, because we cannot use images in the visible range. We have to use radar images to map Venus, because only radar can penetrate the very thick cloud cover of the planet and reach the surface to unveil the beautiful geologic features of the planet. So during this presentation, I will be basically, I will divide this presentation in two parts. In the first part, I will just give a short introduction to what are basically the main parameters to map and also to interpret actually in the right way the radar images for geologic purposes, of course. And this first part will be a little bit theoretical, and I hope not to be too boring. In the second part, instead, I will show you, and this will be probably funnier, I will show you basically a study area that I've been analyzing with my colleagues, and I think it's pretty didactical, especially for the purposes of this presentation. So let's talk about acquisition and interpretation of Magellan radar images, because the Magellan mission was the last mission which analyzed, which performed and made a complete mapping of the surface of Venus in the late 80s and early 90s. And it divided this mapping into three main cycles. So one cycle over left look, where for left look I intend the direction of observation of the radar instrument. So left looking direction mapping in the cycle one. And then there was a cycle two of mapping with the right-looking direction, just to fill the gaps of the cycle one. And then there was a third cycle of mapping just for the stereo pair, so for the stereo coverage. But okay, this cycle just really mapped a very few portions of the surface of Venus. So unfortunately, we don't have stereo coverage for a good part of the Venus surface. So we can see that, for example, cycle one mapped the surface of Venus with a constant incidence angle, which is important, and we will now understand why. And cycle two instead mapped the surface with a more varying incidence angles. So here is, as an example, here is the mosaic of the Magellan cycle one.
Piero, sorry.
Yes.
We are seeing the very first screen. Yeah, I think you are sharing the wrong screen.
Oh, I'm sorry. Okay.
I'm sorry, I didn't follow up.
Maybe it's better if you unshare and share again, because sometimes it's stuck.
Yeah. I hope that it's okay.
I lost the point where you were introducing the presentation.
Oh,
and
I'm sorry. No,
actually, and then we are
yeah,
still
because I
at
was
the very
moving.
same first page. Sorry about that.
No. It's okay. It's okay.
So just to be clear, we are seeing your PowerPoint.
Yeah, the initial, I understand.
Right? Not the slide.
Yes. I think I got, I don't know why I cannot access. Okay.
So we are seeing the
My
app.
computer, no, it seems that my computer is kind of frozen. I think it's better if okay. I will again, I try to share the screen, the desktop. This time should be okay.
Yes, we are seeing the whole screen.
Yes. Okay, now you should be able to see exactly.
Yes.
So it was just acquisition and interpretation of Magellan radar images. Can you see this now?
Yes, perfect.
Okay, great. Sorry for. Okay, so I was saying that the Magellan radar images have been acquired following 3 cycles of observation. So a cycle 1 with the left-looking direction, which basically covered almost the whole surface, and then a cycle 2 with the right-looking direction to fill the gaps of the cycle 1, and then a 3rd cycle for the stereo pairs. But as I said, unfortunately, we have a very poor stereo coverage for the surface of Venus. So I'm indicating now with my mouse the cycle 3. So the cycle 1 was performed with a constant incidence angle, while instead the cycle 2, the cycle 2 was performed with a constant incidence angle, while the cycle 1 had a more varying incidence angle. And you can see here basically as an example, the mosaic of the Magellan cycle 1 coverage. And you can see how the surface of Venus looks on the radar images. So basically, when we map Venus, the most important factor to consider is the radar brightness. So the radar brightness is fundamental when we want to map the surface of Venus. The radar brightness is basically the quantity of energy which is reflected, or let's say using a more technical term, it's scattered back. So the quantity of energy which is scattered back to the instrument, scattered back or not. So basically, the radar brightness is influenced by 3 main factors. So one first factor to influence the radar brightness is the surface roughness. So you can see here, for example, how it works. Basically, the SAR instrument which sends a beam, the radar beam, and we can see also here the local topography, which has also an influence, and we will now tell why. So basically, there are 3 main parameters influencing the radar brightness. So one very important parameter to influence the radar brightness is the surface roughness. So it's the roughness of the target surface, which is basically hit by the radar beam. So if the roughness of the surface compared to the, of course, to the wavelength, to the radar wavelength, if the roughness of the surface is less than the radar wavelength, so the surface appears basically smooth to the radar, then the beam will be basically scattered away from the instrument, so the surface will look dark. For increasingly rough surfaces, we will get also increasing, basically this is the basic rule, we will get also increasing radar brightness. So a good rule on Venus is that usually smoother surfaces on Venus look darker, while rougher surfaces look brighter. This is, I mean, a rule, but there are important exceptions based on latitude and based also on local topography, which is another second parameter to consider when we map the surface of Venus, because local topography, of course, can affect the local incidence angle. And so also local topography can affect in a way the quantity of energy, and so also the brightness of the material we are observing in the radar image. And then there is a third factor influencing the radar brightness, which is the so-called electrical properties of the material, of the target material. So the electric properties are basically the composition. So the composition of the target material is also influencing the radar brightness. So summarizing, the variations in the radar brightness are caused by three main factors. The surface roughness is the main factor to influence the radar brightness, and we have to be very careful to that. And then also there are other two factors, which are, of course, the electrical properties, so basically the composition of the target material, and the topographic effects, intended as a local topography. So let's go now to the funny part, where we will show IMD Regio, which is a very interesting area of Venus. It's basically called the large topographic rise. This region, so large topographic rises on Venus are considered, we can see here, Bel Regio, Isla Regio, Atla Regio. So these are all topographic rises. These regions of Venus are considered to be very important because they are among the youngest regions of the planet. And they are also considered as the surface expression of underlying mantle plumes. So they are very cool regions. And there is one of those, IMD Regio, which is particularly young. And I'm going to show you now, in particular in this region, how we could basically perform a stratigraphic interpretation, a local stratigraphic interpretation of the area, also using not only the volcanic structures and the tectonic features, but also an impact crater. So we can see here the map, and we can see where this, so here is Idun Mons. Basically it's a volcano, it's a young volcano of Venus, which is interacting also with the Chasma, which is basically a rift zone. So we can call it as a volcano rift area, a volcano rift, volcanotectonic system, let's say. And there is this impact crater, which is very interesting. So impact craters on Venus are pretty rare, but in this case, it's very important to show for the didactical reasons of this seminar, because impact craters are characterized by very bright materials. So impact ejecta on Venus are among the brightest, rather brightest materials that we can observe. So basically, we can see really what I mean by rather bright. So we can see, for example, the impact ejecta of this crater, both on the left and right look radar images. They appear very bright because, of course, they are rougher compared, of course, to the radar wavelength. But impact craters are also useful for another reason. I mean, for the didactical purposes of this seminar, because they are characterized by a rather dark halo. So I'm going to basically try to surround it with my mouse. Can you see this halo, this very dark halo compared to the rest of the surface? So basically, this rather dark halo usually indicates young craters. So craters surrounded by a circular halo on Venus are young craters. And craters where the halo is, the rather dark halo is more and more degraded are usually older. So in this case, we can see that, for example, the halo, the rather dark halo of this crater is partially degraded, but still well visible. And also the surface morphology of the crater is, well, it's quite pristine. So we can see that how the radar brightness can help us also to relative dating, for example, in the relative dating. And also the radar brightness of the impact ejecta of this crater, Sandel crater, it's his name, also helped us to recognize and map tectonic fractures and graben. Okay, as you can see, there are these fractures which really disrupt the young impact ejecta of this impact crater. We can see also in the C image, in the C figure, we can also see a graben. So in this way, the radar brightness helps us also to the geologic mapping and the geologic interpretation and in the stratigraphic reconstruction of the area. And we can see the final map, what we could perform. We mapped the Brinker ridges, which are, I will just mention it. They are a stratigraphic marker and a very important stratigraphic marker for Venus. And we can see the dark halo surrounding the impact crater. And we can see also the regional fractures, which in part also disrupt the surface of the craters, also the internal floor of the crater. So allowing basically a local stratigraphic reconstruction. We can also see here how, for example, in the same area, how the lava flows appear on the radar images on Venus. And we can see also a set of tectonic fractures interacting with the lava flows. And we can see in particular that, for example, in some cases, the lava flows overlap the fractures, so bury the fractures. And in other cases, instead, like with the white arrows, the fractures disrupt the lava flows, indicating basically that this area is going through alternating periods of volcanic and tectonic activity. So basically that tectonic and volcanic activity alternate in time in this area. So this is also another example of how we can use the radar brightness and the radar images for geologic interpretation. And finally, we could also reconstruct, as we can see, basically the main aim of the geologic mapping is that, of course, of performing a stratigraphic reconstruction of the area. And we could see, we could place basically Sandel crater, its deposit in the time scale, and also the Brinker ridges. But most importantly, we could conclude in this specific case that the system, so this volcanotectonic system was active before the formation of the crater, but also that the activity is going also after the emplacement of the crater. So this is basically what we can do with the radar images and how we should use the radar brightness in particular to interpret the geology of the surface of Venus. Because in the end, yeah, Venus is the planet where everything burns. Okay, thank you very much.